Chapter 13, Complex Reaction Mechanisms. Section 13.7, Radical Chain Reactions and Radical Chain Polymerization. Radicals are chemical species that contain at least one unpaired electron, such as the hydrogen radical and the hydroxide radical. In the hydrogen radical, we have only one electron, unpaired. In the hydroxide radical, we have a total of 9 electrons. 8 of them are paired, but there's also one unpaired electron. Radicals are often highly reactive. An example of radical-mediated reaction is the thermal decomposition of ethane in the gas phase. So ethane may decompose and form ethylene and H2. The complex mechanism of this reaction may involve 3 stages: initiation, propagation, and termination. In the initiation stage, radicals are produced. In the propagation stage, the number of radicals remain unchanged, but the identity of the radical may change. Termination. Radicals are annihilated in this stage. So now let's look at the 3 different stages of the thermal decomposition of ethane. Initiation. So it's possible to heat up this molecule and break the carbon-carbon hydrogen bond. If we create 2 radicals at the same time, those are 2 methyl radicals. Propagation. There are 3 important propagation reactions. The methyl radical may attack a ethane molecule and abstract a hydrogen off to form CH4 methane. And now we have a different radical, an ethyl radical, C2H5. C2H5 may decompose into ethylene and a hydrogen radical. Now the hydrogen radical can also attack a ethane molecule to form H2 and another ethyl radical. And again, this ethyl radical may decompose into ethylene and a hydrogen radical. In the termination stage, radicals are annihilated. But how? Usually you have 2 radicals reacting with each other, and then all electrons are paired. For example, the hydrogen radical and the ethyl radical may form ethane, or the hydrogen radical may attack this ethyl radical, take away one hydrogen atom, and form H2 and then ethylene. By the way, this hydrogen radical is just the hydrogen atom. There are 3 radicals involved in the thermal decomposition of ethane: the hydrogen radical, the methyl radical, and the ethyl radical. Now we can make steady-state approximation to these 3 radicals. dH over dt is 0, the methyl over dt is 0, the ethyl over dt is 0. Well, this is just because radicals are often highly unstable. The concentrations of these radicals are often extremely low, and then we can make these approximations. Using the 3 equations, we can simplify the differential equations and then express the reaction rate in terms of a constant times the concentration of C2H6. The derivation is non-trivial. It's skipped here. It involves a lot of mathematical detail. I just want to show you, in the end, the consumption rate of C2H6 can be expressed as a constant times its concentration. And now, what are this K1, K3, K4, K5, K6? Alright, it's from the previous page. We have K1 here for initiation. K2, K3, K4 are the propagation steps. K5 and K6 are the termination steps. So we got all those over here combined to form this effective rate constant. So this is a complex reaction mechanism, and we have to use the steady state approximation to solve the differential equations approximately and get this integrated the rate law, and then we can integrate this equations to get the integrated rate law, and this is a pseudo first order reaction. Now let's look at this reaction again. This reaction may also occur in a single elementary step. How is that possible? Well, if you just compare the reactant and the product, well, we just need to break two carbon-hydrogen bonds and form one new hydrogen-hydrogen bond, and then we have the products. So it's possible to draw the transition state structure for this reaction. The transition state should have two partially broken carbon-hydrogen bonds and one partially formed hydrogen-hydrogen bond. And also, well, there should be a carbon-carbon pi bond being partially formed. Sorry about the typo. This should be partially formed. This elementary step has overall a larger reaction barrier than the previously studied complex mechanism, and therefore it has a smaller reaction rate, K sub 7. So this K sub 7 is much smaller than this K sub effective. But if we consider both pathways in parallel, the overall reaction rate should be this. We have K effective plus K7 multiplied by the concentration of SN. But again, keep this in mind, this K7 is much smaller than K effective. So this K7 can be even neglected. But overall, even if we have this expression, it's still a pseudo first order reaction. Combustion reactions are often radical chain reactions. Now let's look at the combustion of methane in oxygen. Also, there are three stages: initiation, propagation, termination. In the initiation stage, radicals are produced. In the propagation stage, the number of radicals remains unchanged. In the termination stage, well, radicals are annihilated. Initiation. So it's possible for one of the carbon-hydrogen bonds to break and form methyl radical and hydrogen radical. With enough energy, we can even break a oxygen-oxygen double bond in O2 to form two oxygen atoms. Propagation. A hydrogen radical may attack a methane molecule and abstract one hydrogen off to form H2. That leaves a methyl radical. The hydrogen radical can also react with oxygen 2 to form hydroxide and an oxygen atom. Hydroxide can attack a methyl molecule to form another methyl radical and water. The methyl radicals can react with the oxygen atom to form formaldehyde and hydrogen atom. Formaldehyde may react with hydroxide to get another radical and water. So all those propagation elementary steps involve the change of the identity of the radicals, but usually the number of radicals remains unchanged. So if you have one radical on the left hand side, you see a radical on the right hand side. It's just these two radicals are different. You see one radical on the left and then one radical on the right. It's just the identity changes. Termination. It's possible for two radicals to form a single bond in between. So the R radical and the hydrogen atom may form RH and release energy. The energy must be taken away by a medium molecule denoted by M. M star denotes the energized medium. Now let's look at radical chain polymerization. It's the polymerization of monomers initiated by radicals. How do we make radicals in the first place? We need radical initiators in this kind of polymerization reactions. Now let's look at the initiation stage. we need a so-called radical initiator and decompose that into two radicals. So it's this elementary step from the initiator I to two radicals R. The rate constant is K sub I. I stands for initiation. For example, benzoyl peroxide is often used as the radical initiator that initiates the radical chain polymerization. The structure is like this. You have a benzene here, and then COO functional group. Same here, benzene COO functional group. And then in the middle, there's a single bond between this COO and this COO. The structure looks like this: two benzene rings, two carbonyl groups, and in the middle you have oxygen single bonded to oxygen. So it's called peroxide. Between these two oxygen, well, the bond is weak due to the repulsion between all those lone pair electrons on the oxygen atoms. So if you heat it, it's going to break the oxygen-oxygen bond to form two radicals. And now we have radicals. The radicals may attack the monomers. So here, a radical reacts with a monomer to form a single bond with the monomer, and it becomes another radical. K1 is the rate constant for this activation step. Here's one example. We can use this radical to attack an ethylene molecule. Now we have a single bond between this oxygen and one of the two carbons in ethylene right here. And then we have, well, a new radical. It's benzene COO CH2 CH2 radical. So the terminal carbon on the right hand side is a radical with one unpaired electron. Now propagation. So once we have a Rm radical, it may react with another monomer to form RMM radical, which then attack another monomer to form RMMM radical. Now we have three monomer units in the polymer. And then we have Rm with n-1 units reacting with another monomer. We have n units. And in general, we use a rate constant K sub P to denote the rate constant for all these reactions because they are similar. It's just a M radical attacking another M, a M radical reacting with another M. Over here, N is just the length of the polymer chain, and again Kp is the rate constant for propagation. K sub P is approximately independent of the polymer length. Now let's look at a few examples. This is the radical reacting with a ethylene. We form this radical. It can react with another ethylene, and now we have a longer carbon chain. And then this longer carbon chain react with another ethylene. We have a even longer carbon chain that contains now 3 ethylene units. Termination involves the recombination between two radicals. For example, if we have two polymer radical chains with a unit length of N and M, well, these two radicals, these two unpaired electrons, may form a single bond in between. Now we have a polymer with a unit length of M plus M. The rate constant is denoted by K sub T. T stands for termination. Here's the example for termination. So if you have a radical chain with 5 monomer units reacting with another radical chain with 4 monomer units, you can get a polymer with a total of 9 monomer units in the middle. Now we're going to study the mechanism of the radical polymerization. We'll treat all radicals as a whole for convenience. We're going to use this notation. This is Rmx. M sub x means we have x monomer units, and this x can be 0, 1, 2, 3. So when I write this, it means we have a R radical, we have RM radical, RMM radical, RMMM radical, RMMMM radical, etc. All of those are denoted by this because they have similar chemical properties. Now the number of these radicals is not affected by the activation reaction or the propagation reaction, because at the activation stage you start from a R radical reacting with an M and you form RM radical. The number of radicals is not changed. In the propagation also, the number of radicals is not changed. Alright? The number of radicals is changed only in the initiation stage and in the termination stage. In the initiation reactions, the number of radicals increases. In the termination reactions, the number of radicals decreases. The radicals are produced in the initiation step. So let's look at this equation. We can see 2 R radicals are produced, and the production rate is 2 times Ki times I, and then multiplied by phi. So why is that? First, we understand the reaction rate is Ki times the concentration of I, so right here. Well, but when 1 I is consumed, we generate 2 R, so we need a 2 here. And also, not every single R can initiate a radical chain reaction. Sometimes this R radical is immediately annihilated for some reason. So here we need to have a new parameter phi. Phi is the probability of R naught or R dot or R radical successfully initiating a radical chain. So that's why what this phi is stands for. Phi is usually lower than 1. The radicals are consumed in the termination reactions. So over here, 2 radicals are annihilated at the same time. So the consumption rate of the radicals is negative 2 K sub T times this squared. Again, we're just treating both M and N as X. X is just more general. We treat this as RMX, we treat this as RMX. So again, we're using RMX as the total concentration of all those radicals. Now we're going to use the steady state approximation to all those radicals. That means the production rate of the radicals is equal to the annihilation rate of the radicals. So we have this 2 phi Kii on the left equals this 2 kT radical squared on the right. So by looking at this equation, we can express the concentration of all radicals easily. 2 and 2 cancel, you move kT to the left hand side and then take the square root. So the concentration of all radicals should be the square root of phi Ki over kT times the concentration of I. Now monomers are consumed in the activation step and also the propagation step. It is also reasonable to assume this K1 is very close to Kp, because if we look at those reactions, they are all reactions between a radical and a monomer, a radical and a monomer. So overall, the consumption rate of M can be considered as negative Kp times M times the total concentration of all radicals. And again, this X can be 0, 1, 2, 3, 4, or 5, or 6, etc. And also we have the expression of this concentration of all radicals from the previous page. It's the square root of phi ki over kti. So we plug in that expression, phi ki over kti, over here. And this is the consumption rate of the monomers, or how fast the monomers are consumed per unit time. The average kinetic chain length for the radical chain polymerization is defined as this. Average kinetic chain length, it's the consumption rate of m of the monomers divided by the production rate of the radicals. So we have the consumption rate of the monomers on top, and we have the production rate of the radicals on the bottom. So it's from 1I to 2R radicals with a rate constant of k sub I and a efficiency of phi. So we have this equation. Now we can clean it up. We get expression for the average kinetic chain length. You just see we have square root of I on top, I on the bottom, square root of ki on top, ki on the bottom, square root of phi on top, and phi on the bottom. So after we clean up this expression, in the end we have this. The average kinetic chain length is kpm over 2 times the square root of phi ki kti. So what's the meaning of this? Well, the average kinetic chain length is this. So assuming within a second 1,000 monomers are consumed, 10 radicals are produced. We're just assuming, this 1,000 monomers are attached to those 10 radicals. And then each radical has a chain length of 1,000 over 10. That's 100. So that's the physical meaning of it. And why do we even care about this average kinetic chain length? Because, this is a instantaneous property. So at given time, you have this average kinetic chain length. And then at different time, you have a different average kinetic chain length. Although this average kinetic chain length changes with time, but overall it gives us a rough understanding of the final average chain length of the polymers. So that's very useful. And we can determine the average kinetic chain length with all those rate constants, the concentration of the monomers, the concentration of the initiator, and also this efficiency phi here. Phi is less than 1. Now we can analyze the average kinetic chain length qualitatively as well. When m is larger, you have a longer chain length. When I is smaller, you have a longer chain length. And also, if kp, the propagation rate constant, is larger, you have a larger chain length. But if the initiation rate constant and the termination rate constant are large, you have a shorter kinetic chain length.